So for a better understanding of the properties of elements, we turn to quantum mechanics and we look at something called electron configurations. Now, in all of what we did in the previous chapter, what we were looking at is the properties of orbitals in a hydrogen atom. So the S, the P, the D, and the F, really those were all developed to describe where the one electron of hydrogen could possibly be found in the atom. But in electron configurations, we sort of extend the idea of orbitals to all atoms. And what we do is we look to see where the electrons are found in all atoms, and then try to use that to help us understand the periodic properties of elements. So a real simple electron configuration to do would be that of hydrogen, because it only has the one electron. Now the 1s orbital is the lowest energy orbital of hydrogen, and so we're going to be doing the electron configuration, but in particular we're doing something called the ground state. And ground state simply means lowest energy state of the atom. So if the 1s orbital is the lowest energy level orbital, then I can put one electron into it, and that would be its electron configuration. So we have the electron configuration for hydrogen, but to understand anything beyond that, what we have to do is we have to look at the experiment that I referred to earlier called the Sterngerlock Experiment. Now you remember in Schrodinger's wave equations, we got three quantum numbers. Those quantum numbers were n, they were n, change color, how's that? Something you can see, which is the principal quantum number, L, which was the angular, principal size, right? Angular shape. It gave us the number of angular nodes. So it gave us the lobes of the shape. And then there was m sub L. And m sub L was the azimuthal. That comes from the idea of an azimuth, or a direction, like where a compass would point, or things like that. So anyways, that gives us the direction, and that tells us how many orbitals there are. And then there was a fourth quantum number, and that's m sub s. And that didn't come from Schrodinger's wave equation, but this was the spin quantum number. So to understand the spin quantum number, we have to go through and look at Sterngerlock experiment just a little bit. So let me briefly set it up as if this, in the Sterngerlock experiment, is if there were a north-south magnet like this. And it's a special magnet, actually. It has a shape to it and everything. But the way the device was set up is, let's say this is north and this is south. It doesn't really matter, but it could be the other way. And then I run a magnet through it that's like this, south, and then north. What happens to this little magnet is that in the Sterngerlock experiment, you'd expect it to be deflected. It creates an upward force. If you switch it, if you go north-south like the other way, this way, then it'll go in this direction. Now, if these are really magnets, like you think about little bar magnets, you could turn them at all kinds of different angles. And as you turn these little bar magnets in different angles, you would actually get a bunch of different trajectories, and there would be a whole bunch of different positions in which you would see the bar magnet striking on a detector, for example. And so that's how the experiment would have worked if electrons really had magnetic moments like little bar magnets, okay? But in fact, when they did the experiment with electrons, some electrons went up, other electrons went down. And so it turns out electrons have magnetic moments, but they're always either in one direction or the other. There's no in between. It's not like the magnetic moment of the electron can be halfway turned. So it's always either spinning up or spinning down. So we use the magnetic moment as a description of the property, but it's not like a little bar magnet. that we're familiar with, where you could turn it and have it be different sort of values. Okay, so in essence, we have two spin states. You can't have like a zero spin state where it's turned sideways. You can either be spinning upward or you could be spinning downward. And this is actually what the Sterngerlock experiment showed us, is that electrons can be sometimes plus 1/2 magnetic moment, so we call that m sub s plus 1/2, or it could be m sub s minus 1/2. And that's the equivalent of having a little magnet pointing up and a little magnet pointing down. And it's more complicated than that, I'm sure, if the physicists got into it. But for the simple chemist, this is good enough. Okay. Now, when you think about magnets, though, and again, we can still use the bar magnet analogy. If I take two bar magnets, and one's north and one's south, and I put another bar magnet next to it that's north and there's south, right? What happens to those two bar magnets? Well, they're going to repel each other. And if you've ever played this game, because as kids you probably played this if you ever holding magnets in a classroom or something, when you let go of one automatically flips over. And you always have one magnet going this way, and you always have another magnet going that way. And the reason it does that is pretty simple. That's the lowest energy. And the lowest energy is when the North Pole and the South Poles are aligned oppositely each other, because of the way the magnetic fields work. For magnets, they're aligning with each other's magnetic fields. And so it turns out, if you're thinking about electron configurations and how electrons go into atoms, we really go back to something that's called an orbital diagram. This represents the 1s orbital, and if I try to stick an electron in it, a second electron in it, this is hydrogen. If I try to do helium, right, then I have to stick a second electron in it, because hydrogen has Z is equal to 1, so it has 1 electron as well. And helium is Z is equal to 2, so it has 2 electrons, because that's what makes it neutral. So if I do helium and I want to stick the second magnet in there, then the question is, how will it go into that orbital? And the answer is pretty straightforward. It has to go like this, because that's the lowest energy for that electron, is to be oriented in the opposite direction than the first one. Now here's the thing. What happens if you try to stick a third electron in here? And remember, electrons can't go in sideways. Like if you could stick an electron in sideways into this box, it might work, because it would be countered by one. The force that it experiences is countered. But with one electron in this system, the force that this one experiences is countered by this one. But electrons don't have that option. They only have a plus or a minus spin. So when you try to stick a second electron into here, a third electron into here. So let's say you want to do lithium, right? You can't stick it in here. And what ends up happening in lithium's case is I have 1s, and then the next lowest energy level orbital is the 2s. And so I can put an electron in here and here. Because remember, lithium is n equals 3, right? And then I can stick the next one in like that. And then if I do beryllium, if you look on the periodic table, beryllium is n equals 4. Then I can go something like this. But guess what? Once I've done that, I don't have space for another electron, so the next lowest orbital is the 2p. And we'll talk more about this as we go along. We'll talk about how we know what all these things will be. But to start with, if I'm writing the electron configurations, then I can write this for hydrogen. I can say hydrogen is 1s1. And that's what I showed over here. Hydrogen is 1s1. Helium would be 1s2, because I have these 2 electrons in the 1s orbital. But if I'm going to do lithium all of a sudden and beryllium, right? Well, lithium is going to be 1s2 and then 2s1, because I can't get all the electrons into the 1s orbital. Once I have 2 into the orbital, that's all I can get. So now it's 1s2, 2s1, and then for beryllium, right? Beryllium will be 1s2 and then 2s2. And as a general rule, when you're putting electrons in orbitals, you only can have 2 electrons per orbital. We'll talk more about, there's names for all these rules. And if you fill up an orbital, then what you have to do is you have to go to the next higher energy level orbital and put an electron into it. So the name of the rule that tells us that you can only have 2 electrons in an orbital is called the Pauli exclusion principle. And it's formalized as a statement. It says no 2 electrons in an atom may have the same set of 4 quantum numbers. So what we're going to show is what the quantum numbers are for each of the electrons in this atom. Okay, so this represents helium. Its electron configuration is 1s2. So the quantum number, the principal quantum number for both is 1. L is the angular quantum number. That'll be 0. Because this represents an s orbital, right? For helium. And m sub L is also 0 because it can only have m sub L can only have one value because it's based on plus or minus L, and since L is 0, m sub L has to be 0. So far these quantum numbers are the same, but where it changes is because we have the spin states of the electrons. So for the first electron, which my computer's decided to change the slide and not let me change it back, I'll do that one in green, let's say. Okay, maybe I won't do it in green. There we go. It's not letting me pick a color. Okay, there you go, green. So we'll do this one in green, right? This is m sub s plus 1/2, and then, yeah, something weird. And we'll do m sub s minus 1/2. We'll do that in orange. So that would be this guy here. This would be minus 1/2, like that. So no 2 electrons in an atom may have the same 4 set of quantum numbers. So if you try to add a third electron in here, so let's say we're going to add in purple, we're going to add this one in here, right? Then what that would have is it would have the exact same quantum numbers as this, because it's spinning upwards and it's in a 1s orbital, right? And as a result, Pauli exclusion principle says you can't have 2 electrons in an atom with the same 4 quantum numbers, so this is excluded from that orbital. Now, that electron then has to go into another orbital. So for example, when we did lithium, we just went ahead and we opened up, is actually the term we use, we opened up the 2s orbital and we stuck the electron in it.